Very happy to introduce Rachel, graduate student graduating this year from MIT. And this is a very exciting work. Even before people knew that Rachel is coming here to talk, I got a couple of emails from different people asking me if anyone is going to speak about this result, because we really want to hear about it. So I'm very happy that Rachel is here and looking forward to the talk.
Oh, thank you. Yeah, so I'll be telling you about a recent work. This is actually going to be about two different works with my wonderful co-authors here. Okay, so what is an expander? So an expander is a graph that is both well-connected and very sparse. Mathematically, you can formalize the notion of expander in a few different ways. Each of the different definitions is good for different applications. Maybe the three most common ways are vertex expansion, spectral expansion, and edge expansion. Vertex expansion, which is what we're going to be talking about today, is going to refer to the fact, to the property that small sets of vertices have many neighbors. Edge expansion will say that there should be no sparse cuts, and spectral expansion asks that there's a large spectral gap between the top and second eigenvalues of the adjacency matrix of the graph. So beyond just like lending themselves to different applications, we also understand these different notions of vertex of expansion to greater or lesser extents. So for instance, we do know constructions of optimal spectral expanders via algebraic and combinatorial methods. And it turns out that optimal spectral expansion does also imply optimal edge expansion up to lower order terms. So in some sense, both spectral expansion and expansion we have pretty good handholds on. On the other hand, vertex expansion is kind of the oddball out in the sense that like really good spectral expansion will imply a little bit of vertex expansion, which I'll tell you about in a bit, but it won't actually imply optimal vertex expansion. So today's focus of the talk is going to be on this like third property of the vertex expansion, which we didn't previously know how to construct explicitly. Okay, and then before we really get started, there have been many applications of vertex expanders. Here's some of them. If you know more, please let me know. I'm always looking to add to this list. Yeah, and so hopefully there's something for most of you here. Like hopefully something here looks interesting. But beyond just like TCS applications, I also do want to advertise that lossless expanders are actually of general interest. So this is an ad that Spotify launched in September last month. It says, your music is about to sound better. Lossless, they forgot the expanders part, but it's clearly implied, is coming to premium and will notify you when it's available. And then a couple weeks ago, they actually launched lossless. So anyway, so it's a very exciting time to be talking about this. Cool. So what is a vertex expander? A vertex expander, I will say that a graph is a vertex expander if every not too large set of vertices has many neighbors. So here's a D-regular graph, and here's a set S. So the set S, each vertex is going to have degree D. So coming out of it, there's going to be D times size of S number of neighbors. Number of edges, coming out of it. These could hit some neighborhood, which are called N of S. And ideally, you'll have like a large number of neighbors, ideally as many as there are edges. And we'll denote the expansion of the set S to be equal to the size of the neighborhood over the number of edges. So ideally, we'd like this expansion to be as close to 1 as possible. So if we constant between 0 and 1, we want to be as close to 1 as possible. And we'll say that the graph is a lossless expander if the expansion of every set is very close to 1 for every small set of constant like linear size. So yeah, in general, like we want the size of the set to be some small constant. It can depend on D. You think of it as like 1 over D or 1 over poly D. Okay, so what do we know about vertex expanders? Well, we know if we take a random graph, we will get a lossless expander with high probability. But what about explicit constructions? Okay, before we talk about what we know, maybe we should say, why do we even care about this question? Well, one is a nice mathematical question. But more than that, even though we know how to sample, even though we know that a random graph is with high probability a lossless expander, we don't know how to check that a given graph is actually a good vertex expander.
Can you
Secondly,
say a word about random graphs? I mean, is it obvious? I mean,
Yeah, you can just-
I thought about it.
Yeah,
This is obvious, much more is known. I mean, you really get a factor of expansion D minus 2. D minus, so as the S will see D minus 2 times S neighbors is much better than 1 minus. Let's say if the set is less than 1, we'll just.
Yeah, I guess a tree will give me D minus 1, so like a ball, so I can't expect
Yeah, yes, in fact, you can get D minus 1 minus epsilon.
minus epsilon.
Yeah,
I can't expect better than D minus
Yeah.
1 because there's always the edge going back inside the ball,
absolutely.
and you just get above that.
You get about the calculation is made this monograph with the Nazi and normal.
You do this
Yeah,
calculation.
we do the calculation, yeah.
So I should think of this epsilon as some constant dependent on D or
Probably not.
yeah, so I think, yeah, the way we're gonna model it is you think of, you fix epsilon very close to 0, and then you can pick D depending on epsilon. The best you can hope for is,
and also you have this eta, right?
yeah, the eta, just think of it as 1 over poly D. We won't talk about that as much. It's gonna be some small constant depending on what D is.
Okay.
Yeah, I guess random graphs will get you D equals 1 over epsilon. We won't get quite that good of a trade-off, or actually not even nearly as good a trade-off.
Maybe also to say that eta cannot be better than,
Cannot be better than 1 over D, because if you have a, 1 over D fraction of vertices and each has degree D, well, you'll have too many edges for the number of vertices. Cool. So yeah, so one reason we care about explicit constructions is I guess we don't know how to even certify that a given graph is a good vertex expander. The second thing is that oftentimes for applications, we will want our expanders to have some additional structure. And random graphs will often lack this structure. For instance, for this application of quantum LDPC codes by Hsieh, in which you need your loss expanders to additionally have a nearly transitive group action. This we don't know for random graphs or for any algebraic graphs.
also for random Cayley graphs, this is.
Yeah, we don't know how to do this. We don't know how to say it. So I mentioned earlier that spectral expansion will give you some vertex expansion. Maybe let's look at what that gives. First of all, a spectral expander is a graph in which the second eigenvalue is much less than the top eigenvalue. Spectral expanders are powerful. They imply many useful properties. We know a lot of constructions of these objects. So what kind of vertex expansion do you get from spectral expansion? Well, in 95, Hsieh showed that if you have Ramanujan graphs, which are optimal spectral expanders, you get 1/2 vertex expansion as well. Unfortunately, this is also actually tight. So there are, in fact, Ramanujan graphs that get exactly 1/2 vertex expansion. So there probably are Ramanujan graphs that are loss expanders. We don't know how to show it. What I'm trying to say is that the property of good spectral expansion does not, as itself, imply the property of strong vertex expansion. So we don't know how to. We still don't know how to get loss expansion from the spectral expanders. It turns out that until our recent works, this was the best we knew. So we call this a spectral barrier. So this was at 1/2. This is the best we knew before. And the question obviously is can we beat 1/2? And if we could beat 1/2, there would be some implications. Let me just tell you some implications for error correcting codes. So if you could get just a one-sided greater than 1/2 vertex expansion, you can get good error correcting codes by Sipser and Spielman. And then Hsieh showed that if you can actually get unsided, just like the general case, greater than 11/12 vertex expansion, you can get good quantum LTVC codes. I also want to mention that there have been weaker variants that have been studied. So one variant is one-sided loss expansion, where you have a bipartite graph and you only have expansion from sets on the left to the sets on the right. So it will be one directional. There's also been studies of unique neighbor expansion, which is, I guess you want to just show that there are some neighbors on the right or some neighbors that are only hit exactly once. There's also been studied in an imbalanced setting where your left side is polynomially larger than your right side. And also there's been people studied small polynomial or subpolynomial sets, expansion for these small sets. want to mention none of these weaker variants will give you the quantum LDPC code application. So for instance, for the imbalance setting, if you plug in those constructions, you'll get some codes with like square root degree, which is not constant, it's like much larger than constant, in fact. And then if you use these works for a small polynomial or subpolynomial sets, you'll get small polynomial or subpolynomial distance. So also won't be good for QLDPC codes. Yeah.
If you get a vertex expander beyond this spectral barrier, is it also a Ramanujan graph?
Not necessarily. So our graphs actually are not Ramanujan expanders.
So it's incomparable.
Yeah.
There are inequalities. Some parameter here implies some parameter here, but never in the optic.
Like even in this 1 minus epsilon.
Yeah, no.
Okay.
Wait, can't a disconnected graph also be a vertex expander for like small n of t?
Right.
Okay, so what do we show? In the first work, we break the spectral barrier and we construct 3/5 vertex expanders. And then in the second work, we push it all the way up to lossless. Our graphs also have the special group action I mentioned earlier that you need to instantiate the QLDPC application. So more generally, our graphs are going to have this bipartite form where sets on the left, expansion sets on the right, and sets on the right, expansion sets on the left. Our result also extends for biregular graphs. So we can choose constant imbalance, and then you can pick large enough C and D for which you can construct such also expanders, expansion from left to right and right to left.
So your construction is biregular. Is it bipartite always, or?
It's as written as bipartite, but I think you can easily generalize it to like tripartite, or like you can add more parts if you want. There's like a way.
Or not bipartite? I mean.
So I mean, the way we've written is bipartite, yeah. But like any small sets, you can split into like sets on the left and sets on the right, and expansion from left to right and right to left will imply general expansion.
Like, what about like length two paths in your construction and you focus on one side, would that still be a lossless expander?
If S is sufficiently small, sure. By definition.
That's clear, right? So then it won't be bipartite.
Okay, then yeah, then you can also get that. Okay. Nice. Okay, so maybe let me tell you what our construction looks like. So let me start with a high-level strategy. So we already observed that random graphs are lossless expanders. We can't sample a big random graph and check it, but what we can do is we can find a small instance via exhaustive search. So let's suppose that we found such an instance. It will be on D by D vertices, unless it has degree DH. And the idea is going to be, we're going to take our gadget, we're going to call this a gadget graph. We're going to take our gadget graph and lay it in via some blueprint, such that the way you lay it will let you argue that you can actually, that the global graph will be a loss expander as well. So how do we do that? So the general framework is going to be what we're going to call the tripartite line product. So here our graph is there's going to be 3 sets of vertices, a left, a middle, and a right. The final graph we're going to have is going to only have vertices L and R. The middle set is just there to help inform the construction. L and M are related by a graph GL. It's going to be K by capital D by regular. And then M and R are going to be connected by a graph GR, which is going to be D by K by regular. Here you should think of K as being, K and D are both constants. K is much smaller than D. And we'll call GL and GR our base graphs. So now, given these base graphs, they're going to be our blueprints for overlaying the gadget graphs. What we're going to do is we're going to take every single middle vertex, look at its left neighbors and its right neighbors. There are capital D of either, and we're going to place a copy of our gadget graph between the 2 sets. Okay. And I drew it here just for one, but we're really going to do it for all the different middle vertices.
How did you choose the left and M and R?
I'll tell you in a second. So this is like the general framework. I haven't told you what the base graphs are, but that would be kind of the much of the rest of the talk. Cool. And then the graph we get is going to be the graph which consists of the left vertices, the right vertices, and all the red edges. We're going to throw away M, GL, and GR. Notice that this is KDH by KDH by regular. Why? Because if you look at a vertex, it participates in has K different neighbors in the middle. So it's going to participate in K different gadget graphs. In each gadget graph, it has degree DH. So it's going to have degree K times H. Okay. So now let me tell you what the base graph is. So I guess okay, so maybe what would you want to choose for a base graph? Maybe you should pick the best expander we know, right? So the best expander we know are Ramanujan graphs. Unfortunately, it seems like the spectral properties of Ramanujan graphs by themselves are not going to be enough to argue good vertex expansion. So our idea is to use some higher dimensional structure. Namely, in our first work, we use base graphs that are constructed from the Ramanujan complex, from which we obtain 3/5 vertex expansion. In our second work, we use base graphs constructed from the Ramanujan cubical complex, which we can use to argue lossless expansion. So for the rest of this talk, I want to focus on this latter work. So maybe let me just start and tell you what the cubical complex is. Okay, so what is a cubical complex? Let's start with one-dimensional. One-dimensional, it should be pretty familiar. So a one-dimensional cubical complex is just a KB graph. Okay, namely, let's take a group gamma and a generator set A. So the 1D cubical complex is going to consist of two sets of vertices. So usually KB graphs you only have one, but let's say there's two, just to generalize better that way. There's two copies of your group as vertices. And then the edges, for every G here on the left, we're going to place an edge between GA for all the generators A. Yeah, and similarly, if you count the degrees, you'll see that every right vertex also has the same number of returning neighbors to the left.
It's not the usual definition of a cubical complex.
Yeah, this is maybe, this is a 1D version, so let me just generalize it just to.
Yeah, no, I'm saying just usually cubical complex is any graph.
Okay.
I mean, it's much more general.
There's a whole theory of cubical complexes, it's a kind of geometric theory, and this is not exactly the same
Oh, I see, okay.
definition, so kind of.
There's cube complex and cubical.
But this is what you were saying about it.
Yeah, but her definition is
Yeah.
specific,
I
it
agree.
doesn't have to do with.
Yeah, it's not cube, it's not a
It's
cube.
cat
complex.
zero cube complexes, it's something else.
Okay.
Okay. And just note that every vertex is contained in A different edges. That good? Okay. Let's go to 2D now. So for 2D cubical complexes, we'll have again a single group gamma and two generator sets A1 and A2. In the 2D cubical complex, we're now going to have 4 copies of the group as vertices. In the horizontal directions, we're going to place a copy of the A1 Cayley graph. In the vertical directions, we're going to place a copy of the A2 Cayley graph. So here, so far, we have vertices and edges. This is 2D complex, so we're also going to have squares. And squares are going to just be a set of kind of 4 vertices with edges going between them. So the squares that really arise from the edges that we've placed.
But these are both Katie graphs from the same side, right?
Yes, they're from the same side, yes. Yeah. And we want there to be many squares. So this is guaranteed by something that's called the cubical property, which will say that for, if you start with a group element here, G, and you choose an A1 and then an A2, there's a unique way you could have instead gone up to A2 prime and then A1 prime. So you have this kind of commuting kind of definition that's according to sets in a sense. Notice this property is actually pretty easy for abelian groups, right? Because you can just choose A2 equals A2 and A1 equals A1. But for us, but for abelian graphs, for abelian groups, you can only get log n size generating sets. We're going to want constant degree, so we're going to have to kind of choose we're gonna have to use some special groups that have both Ramanujan expansion and also constant generating sets. Yeah, and then maybe let's do a count really fast. So note that for every single group element, there's a kind of a unique cube that arises from a choice of A1 generator and A2 generator. So the total number of squares each vertex is contained in is A1 times A2. Let's go up one more dimension. So 3D. Again, a group gamma, 3 generator sets this time. Our 3D cubical complex is going to consist of 8 copies of gamma. Each of the 3 directions, we're going to place a copy of the corresponding Cayley graph. And the cubes are just going to be the cubes that arise in this graph. And the cubical properties this time will say that for any choice of A1, A2, and A3, there's a unique way to complete it to a full cube. And if we do a count, you can see that every vertex is contained in exactly A1 times A2 times A3 number of cubes. All right. So now that we have the cubical complex, let's return to our question of what our base graph is. Oh, sorry, actually, no, let's not do that yet. Let's talk a bit more about the cubical complex. So let me just say a few words about the cubical complex. So first, as I mentioned, abelian groups will have the cubical property where the generating sets have size log n. We are going to want constant degree. So instead, we're going to use a non-abelian Ramanujan cubical complex. These Ramanujan cubical complexes will have constant size generator sets. And also for any sort of adjacent pairs, like the resulting Cayley graph has Ramanujan expansion.
Can I ask something about the first clause? Like, when you mean omega of log n, you mean that I need these many generators. Like clearly it will have the cubical property in the sense of commutation, but for it to have extra conditions, yeah, like you need expansion.
If you want an expansion.
Even connectivity.
Even for connectivity.
No, because I can take a cyclic group, a
Yeah,
huge
yeah.
cyclic abelian group, and then for connectivity I
Yeah.
can have one
Actually,
generator.
That's right, yeah.
So
Yeah,
No, for
but for expansion, for actual expansion.
The uniqueness is. So the uniqueness.
You need to think about it, right? You need to choose the generator such that it's unique, yeah.
Should
It's also
be a data.
potentially tricky.
It's not very important.
Yeah, no. it's,
If you want expansion, you can take
Try to
it to be
understand.
bigger also, like more will only help kind of. So.
So what is the resulting JL0?
Okay. Yeah, okay. Actually, you might know more about like this whole theory of cubical
What is
complexes.
JL and what's?
There's
so-
Jordan and Livne.
Yeah.
Okay,
It's
yeah.
this generalization of LPS expanders by having multiple
Yeah,
sets of
but maybe you
generators.
know it.
Yeah.
The Jordan and Lebanon RSV,
Or what?
RSV.
Yeah, I was also one of the core hard.
Oh, yeah.
yeah.
I don't actually remember, so I have to look it up. I'm sorry.
Write it explicitly on the slide.
Yeah, no, I should have. Sorry. Yeah. Yeah, and then our cubical complexes you can construct using the LPS Cayley graphs. Okay. Just a comparison to other complexes that have appeared recently in the literature. So I guess there were the left-right Cayley complexes due to Irit et al. These unfortunately are only 2-dimensional. The way they work is you kind of left multiply and right multiply. There's only 2 sides, right? So you can only have 2 dimensions. There's also these cubical complexes of Irit, David, and Thomas that they use to construct QLTC codes. These are, I guess, like basically R complexes, but the abelian version. So, and they really rely on the group itself being abelian. And as a result, they'll get some logarithmic loss in parameters. For us, we're going to want general higher dimensional. And then we're also going to want constant degree.
See, let me just say something just to clarify. In our complexes and also the ones we used with for the quantum codes, the cubical property we had is A1 time going A1 and then A2 is the same as going the same generators, A2 and then A1. And that was very important for defining the codes inside. And here, since you don't need to define these extra codes, you can afford to use different generators.
So in this sense, like you can't just plug in these cubes in the previous works and to get something something better.
Yeah, you cannot like define LTCs on these objects. As far as we.
Yeah.
This is because the neighborhoods don't see each other in the right way.
You don't have ways to.
Sorry. What?
Right, you can't.
Okay, so now let's return to our base graph.
Sorry, can you say more about like the final comments? Like,
Oh, yeah, I guess like just compared to the previous two, so we want general arbitrary dimensional. So these won't work, and then we need constant degree, so we need a non-Euclidean version.
But I thought you only use 3 dimensions.
Oh, sorry, well, yeah, we'll generalize it, sorry. So 1, 2, 3, and then you can induct,
Okay.
yeah.
What should I think of K as?
K, I think for us is like 1/epsilon squared or something. Yeah, so it's gonna be like a fairly large, it's gonna be a larger constant as epsilon goes to 0. But D is gonna be a much larger constant than K. Okay, so now that we know what cubical complexes are, let's talk about our base graphs. So cubical complexes, let's think of it as a set of vertices and a set of cubes. So the vertices are on these like, 2 to the k different, 2 to the k minus 1 different parts, and the cubes are the resulting cube that arise in the cubical complex. In our base graph, we're going to place all the cubes of the cubical complex on the left and the right. Okay, want to reiterate that each cube is a single entity. So this is like a vertex in this this whole base graph, this whole left side, and a number of such things. The ways that you can choose a cube is you can pick a group element in like the bottom left, and then you can send it to a cube in this many different ways. Okay, the middle we're going to place vertices. We're not going to place all the vertices. We're only going to place the vertices according to a select number of parts in the cubical complex. So then according to the Hadamard code. I guess like the notable property is that every pair is like distance 2 away, right? It's like a very balanced form. So we're going to take these 4 parts and we're going to place those vertices in the middle. So there should be in general k times the size of gamma number of vertices.
I think you really think the other mark.
You can take any epsilon balance code if you want. Just like some, yeah.
Yeah.
Yeah, so we didn't optimize it. Yeah.
So K is not a dimension?
Yeah, so I guess, yeah, so this is a bit of a weird thing because it's like an off by 1 error. I decided to make K the degree from the cubes to the middle. So here would be K equals 4. Let me tell you one in a second. But then, yeah, and then dimension would be K minus 1. Okay. So here the dimension is 3 and like the K, like the left to middle degree would be 4. Okay, yeah, so the way we connect cubes to vertices is by inclusion. Like you just connect every cube to each of the K different vertices that it contains.
Wait, just a bit more slowly about the middle guy. For every Hadamard code word, you have a copy here?
Yes.
In Hadamard code word, it's just a
How many
growth of the
code-
Hadamard matrix.
how many code words do we have?
No.
There's gonna be, if you have like K
No,
minus
right.
1 dimensions, you'll have K of them.
So K is like the 2 to the something, which is the
Yes,
length of the
yes,
Hadamard code.
yes. Yeah.
Yeah, you should say what the Hadamard code is. because
Okay.
Not everyone knows.
Yeah, so the Hadamard code is, I mean, I think the really important part is that if you look at any pair of parts, these blue parts that we included, there's the same distance between them. There's like distance K over 2. In this case, it's just distance 3. Right, so it's a very balancing, like no matter if you want to go from here to here or here to here, they're all the same distance apart.
And kind of maximally.
Maximally so, yeah. And then in general, we're going to connect every cube to the vertices it contains in the middle. So that's our base. Oh wait, let's do it to ND check. So the degree from the cubes to the vertices is 4 in this case, right? In this specific 3-dimensional example, because there's 4 different vertices you're connecting to. And the degree from a vertex to cubes is a number of cubes that contain the vertex, right? So it's going to be A1 times A2 times A3. Similarly, the side is going to be the opposite, symmetrical.
Sorry, I'm still not seeing it, so, the 4 blue circles in the middle, they're just copies of each other, there's no twisting or anything,
Yeah.
right? So every cube has a specific place where it connects to. And the same one goes on the other side.
And in general, we'll have degrees K and then the product of A1 up to AK minus 1.
Wait, why is it degree K?
Good, okay. This is, I guess, a Hadamard code. Maybe I should pin it down somewhere, but like the Hadamard code, we're gonna pick, so K is gonna be a power of 2. And then the number of code words is always gonna be equal to K. And the dimension is equal to K minus 1.
So that one code just chooses half of the element.
That's not gonna be half, it's gonna be like log, yeah.
Log, like out of a cube of size 2 to the k, you choose k vertices with the property that each one of them is k minus 1 away.
Into
or
the
k
3
minus-
Ks, okay.
Yeah, it's gonna be the
Ah,
distance.
yeah, like here she takes the Hadamard code 1 dimension up and the commentary.
Yeah, actually, can you write on the board
Yeah.
something that's not like with the k equals 2, but rather a
Yeah,
general?
yeah.
I don't see if 4 is log of something or it's half of something.
It's
yeah,
power
yeah.
of 2, no?
Okay, so,
K is over. It's the number of elements.
Still, like the number of pink vertices inside a cube.
the dimension is,
The number.
No, that's just half.
In the circles, you have the whole group.
She's right that here the dimension is not compatible. Somehow
You're
we lost
saying
1
K
dimension.
minus 1 has to be a power of 2?
K is a power of 2. And then, the distance between any 2 code words, is equal to K over 2.
Maybe my question was the pink vertices. Am I supposed to think of each vertex as a string in the Hadamard code? As like a coordinate in the Hadamard code?
Okay,
So we
I guess the pink vertices are group elements. Right, like these are all, like these cubes, these are all group elements.
No, but this, it's okay. This is like the 0, 0, 0, 0, 0 element.
Oh, yeah,
Which is
sorry,
in the,
yeah.
like, this is in the Hadamard code of dimension up if you add a 0 at the end. I think these are the cubes. These are strings of length k minus 1. If you add a 0 in the end, you're either in the Hadamard code of that one dimension up or not. That will decide whether you're a pink vertex or not.
Okay, so a pink vertex, sorry, is a string which is black if it's not part of the Hadamard code, and it's pink if it's in the Hadamard. Right, so what Michael said is right, that there's like logarithmically many of them. Inside a cube of 2 to the k vertices, only log of them are the ones that are kind of nicely separated and not
Yeah.
k of them. And
No, she.
Okay, logarithmic
yeah,
of 2 to the k.
Yeah.
Okay, sorry, it's just,
I don't think that like the correct me if I'm wrong. A vertex is a blob of like these little pink and black dots, right?
So on the left and the middle, the vertices are cubes, like these are each a single.
Right, sorry, I meant that in the left, the vertices are cubes. In the right, the vertices are
Cubes as well.
not the right, sorry, in the middle,
The vertices are original vertices,
sure.
but not out of all possible.
Right. In the middle, sorry, the vertices which are represented in this picture by blobs, right, are.
Oh, sorry, these are all sets of vertices. These are each a copy of the group. This.
No, each vertex is a vertex of the original blob.
Oh, I see. So each blob is one part of this like 2 to the k part-8 things, but we're only taking the parts that belong to strings that are part of the Hadamard code word. And now this picture, what it's telling me is that if I have a cube, I mean, it's just containment, but I'm only taking part of the parts, right? That's all.
I'm confused about the Hadamard code. Why the dimension is k minus 1?
Forgets the last bit and forces it to be zero.
So the dimension is like the dimension of the code was.
No, she just tries to embed something that is induced by one dimension up into one dimension down. So you agree with me that a k minus one dimensional cube is k minus one is a string of k minus one bits, right? Now I'm trying to induce a Hadamard code on this thing, so I add one bit, and then you're in the actual Hadamard code of this thing, right?
Sorry, okay, yeah, I think there's a whole confusion with K minus one versus K.
I'm
No. Yeah, I think you're right, but like, I think the real reason there's this K minus one versus K confusion is I can't draw in 4D. So like I could draw in 3D. Like I guess if you want to make it like simpler, you can just think of it as like this is a 4D thing, and then you just take the Hadamard code and you forget about the K minus one.
There is a 4-dimensional group there, you just don't see.
So there's more stuff out here that's Is everyone okay on the construction? Yeah.
The edges to the middle part are just like if that vertex touches the cube.
Yeah, if it's in the cube, yeah. Okay. Cool. So let's go back to our expander now. So this is our base graph. And recall the way we complete this to an expander is we're going to take every middle vertex. We're going to look at the cube on the left and on the right, and we're going to place a gadget graph between the two sets of cubes. Okay. And that's our resulting graph. It has degree kdh. Again, just to remind you why each cube is going to look at, in this case, 4 or k different neighbors in the middle. Each gadget is going to contribute a degree of these.
Okay, so now I want to say, the way I understand it, if I don't, forget about this picture for a minute, and I just think of the cube complex, and I think of the cubes as objects, then it's like I move from one cube to another by choosing a Hadamard code word and kind of flipping on that,
Yes.
on those like generators according to what the Hadamard code word tells me. And that's how I go to another cube, but then that's before introducing the gadget. That's if I would have done like going through the dotted lines.
Yeah.
And then you replace this like two-step walk by a gadget.
Yes, you're sparsifying like the two-step walk.
Sparsifying.
Yeah, exactly.
Rachel, it's also true that like you can't go, like there is only one way, before the gadget, there's only one way to go from cube to cube, right? Like you can't by accident go like from cube number 1 to cube number 2 via 2 different middle vertices, right? Because of the Hadamard property.
No, that's not true,
No.
because if you have 2 vertices, they are contained in many different cubes.
Even if they're like
Yes.
maximally apart.
Yeah, I guess
You
even,
meant if you have 2 cubes,
Right, that's what I
there's
said.
only not 2 vertices.
no, yeah, there's 2 cubes, there can be many ways, right? If you consider like, okay, so from this cube, you can go to this vertex, or you can go to this vertex.
Right, that's right.
And then if you want to then complete this back to a cube, there's many ways you can choose this up direction.
Oh, I see. No, but there's many ways you can choose this up. My question is this, we're saying that this thing is regular, right? So doesn't this mean that in particular you want no intersections or something? Like, or you're thinking of multi-edges?
Okay, yes, I guess. Yeah, so we don't, I guess we never wrote out the case as there are no multi-edges, so I need to think about it, but I think maybe you can just argue like some probabilistic thing going on with the gadget, you could maybe argue that that sort of thing can happen, but we didn't do it. So we have multi-edges in our graph.
Okay, so you have one, okay.
But if you have 2 cubes that like, I don't know, share like the bottom little part, right?
Yeah.
And they will like go to the same 2, they will like or they will share multiple middle vertices, right?
I see them puzzled about the connection with the gadget graph. The vertices of the gadget graph are cubes or vertices?
They are cubes. Yeah, so maybe in the gadget graph picture, these 3 should all be cubes.
Like if you subscribe to some high dimensional way to describe it, you are describing a walk between cube to cube, and then you're sparsifying.
Yes. Okay, cool. So that's like the construction. I guess the rest, I wanted to tell you a bit about why this works. But if you guys have more questions, we should focus on this first. Yeah.
Just a small question, maybe like this sparsifying scheme assumes some order on the cubes, right?
Yes.
Like, and that's
Yes,
just
and that's-
false some order.
That will be because our underlying base graphs will have some like group action, like it'll have some group structure. So and it's like a Cayley structure, so you can order the different neighbors by like the corresponding Cayley generator.
What is the group gap?
It's what's like the LPS graph?
It's like a SM2 or something like that. SM2 by 2
Google
matrix.
matrices, so we're finding through.
But you choose K different generating sets for these
Yeah, and
groups?
it's actually not like
The
over
border.
ZP, you need to take extensions of this field so that you have like sets of generators that kind of don't interact with each other.
It's not just a direct product, but
No.
okay, no.
You can take like several different primes, but then you don't want primes at different sizes. I don't know if you guys.
The primes will have slightly different sizes, but they'll all be kind of within a
Kind of
epsilon
within-
radius
okay.
together. Yeah.
And Rachel, it's important to you that these things will be Ramanujan, right? Not just like,
Or at least very close to it. Like, yeah, probably need to be within like the second eigenvalue should be like d to the. Okay, let's just say 1/2 plus epsilon, and like the epsilon can maybe be like a actual constant, but it should be pretty close to 1/2. Yeah,
but it can't be like 3/4.
no, that's too big. Yeah.
You didn't explain where you use spectral expansion here, right?
Have not, yes.
Yeah.
Have not touched. I just told you the construction. Haven't told you anything about why it works. Should we move on, or any more questions about this? Okay. Great. Oh yeah, maybe let me also just mention briefly this why we have this Hadamard restriction. Okay, then this is very vague. So the analysis involves some delicate balance of parameters. Really what this Hadamard restriction does, it is symmetrizes a complex. So I said earlier, like every 2 parts will have distance exactly 2 now. Right, so like your view from any vertex will be kind of the same, like all the other numbers will look the same from this point of view. So, okay, cool, it's analysis. Okay, so our goal is to show that small sets of cubes have many neighbors. It suffices, by symmetry, suffices is to show this property for small sets on just the left side. So we want to show expansion from left to right. Recall that we said that each cube sends out kdh different edges to the right. Our goal is to show that these edges will hit this number 1 minus epsilon fraction of different cubes. In other words, we want to show that these edges have many unique neighbors. Unique neighbors are cubes that are hit exactly once, and very few collisions. So these are collisions where they were hit more than once, and these are like, I guess, won't add to your count.
Many is almost all.
Many isn't almost all, yeah. So this is like 1 minus epsilon, and this is like epsilon fraction. Okay. So let's recall. Okay, so we want to avoid collisions. Let's recall where these edges came from. So let's look at a single cube. Recall that the edges coming out of this cube came from k different gadgets, right? Corresponding to the k middle vertices is adjacent to. Cool. So if you think about it a bit, there's kind of 2 ways that you can have collisions. The first way is you can have collisions that come from within the same gadget. And the second way is you can get collisions that come from between different gadgets. Okay. So we'd like to limit or bound both types of collisions.
Gadgets really have to refer in this case to the right part, the right base graph.
Sorry, say again.
When you say the gadget, it really lives on the right base graph.
No, the gadget is between the left and the right. It's like between the left neighborhood of a middle vertex and the right neighborhood.
Okay.
Yeah, so every middle vertex will have a gadget around it, and then we want to look at collisions.
You have a factor of k over the dh. Because every cube has sense k.
Yeah, sorry, yeah. So every cube has participants in k different gadgets. Each one has
Yeah.
degree dh. Yeah, exactly. So let's start with the first type of collision, collisions within the same gadget. Okay. So let's look at a few different examples of possible gadgets. Okay. One type of gadget you might have might only have one cube in S. Okay, so this cube is going to send out DH different neighbors. These are all going to go, you chose this gadget graph, well, so these are all going to different places, right? So there's no collisions within the same gadget. Okay, so we're happy right now. Once you start going up in terms of the number of cubes in S, you start getting the possibility of some collisions, right? Assuming we chose a gadget graph to be lossless, so you actually won't get very many. Most of these things will still get go to different cubes. You only get almost like a maybe epsilon fraction of collisions. Okay, so still we're pretty happy. Things start going.
Okay, I mean, unless it's too much.
Yes, that's where we're going. Yeah, so things start going wrong once you have gadgets that have more than D over DH many neighbors back in S. Okay. Why do things start going wrong? Remember our gadget graph we picked to be on D by D, I guess cubes in this case, these should be cubes. And if you have a set of size greater than D over DH, each of those cubes is going to send out DH different edges. But the whole right side here was only size D, so you'd have too many edges for the number of vertices to expand to. They start getting a lot of collisions. Okay. So we'll call a set of such vertices, such gadgets with too many left neighbors in S, the set of bad gadgets. These are the ones where we won't experience many unique neighbors. And we'll call the rest of the gadgets the good gadgets. These are the ones that have few enough cubes in S to experience lossless expansion. And our high-level goal is going to be show that most cubes in S will partake in many good gadgets and very few bad gadgets. Yeah.
What if the gadgets like overlap?
Yeah, they could. On the right-hand side, or
Yeah, on the right-hand side.
So that's like going to be the second type. Is it going to be collision?
Oh, sorry, we're in.
Yeah. So we're in the first case right now, but yeah, that's a yes, great observation. Cool. So, so how do we do that? Okay, so I guess, maybe ideally, like something you could like really optimistically hope to show is that there's no bad gadgets at all. That would be really good, right? If you could just show no bad gadgets, we'd be very happy. That's not going to be possible though. For instance, if you picked a single gadget and you took S to just be all of the left neighbors, right? Then all of these cubes are going to partake in at least one bad gadget, namely the one corresponding to you. So you're never going to be able to completely avoid bad gadgets. What you can hope to show though, is that, okay, each of these cubes has k different neighbors. One of them was bad, but maybe you can show the other k minus one are all good. Okay, that'd be great.
That edge expansion is enough for that. Or the Ramanujan.
Yes, just spectral expansion will kind of give you some sort of behavior like this. This is actually going to be a bit stronger than what we're going to be able to use later. So maybe let me weaken this a little bit, and we're going to want to show that maybe most cubes partake in mostly good gadgets. So like 1 minus epsilon fraction of good gadgets, and very few, like a less than epsilon fraction of bad gadgets. Cool. So how do we argue something like this? Let's look at the bad gadget condition. We want to show that all these cubes partake in less than epsilon k bad gadgets. So kind of a bad configuration for us would be the following. It'd be one where each of these cubes partakes in greater than epsilon k different bad gadgets. And the right degree is going to be bigger than d over dh. Why? Because that's how we define the set bad, right? So bad has are the ones with greater than d over dh many neighbors in S. So we'd like to rule out this sort of subgraph in our cubical complex. Okay, how do we rule this sort of thing out? Well, let's look at maybe just our set here. Let's call this set U. And let's look at all of the different cubes which have at least epsilon k neighbors within U. Okay, and let's call this quantity, like so this quantity here is like the average number of such cubes each vertex in U sees. Okay, so this is like mimicking the right degree. So it's like the maximum, I guess of cubes with, epsilon k vertices in U over the size of U. We'll call this quantity the subcube density.
So this runs over all small subsets of the right-hand side of this.
Yes. Yeah. It's like, yeah, so like, you know, you're maybe looking for a bad set and like you can try many different U's which are like the potential bad set. If you can say that this quantity is less than d over dh, then actually this can't be a bad set, right? Because this degree here could not have been as big as d over dh. Okay. So notice this is a property of the cubical complex. We can compute this property, or you can try to compute it using spectral bounds. You can get an upper bound for this quantity. So place an upper bound on the value of dh. So dh, okay. So in particular, when you choose a value of dh, this is the gadget degree. You can choose it to be anything between 0 and capital D. Capital D is the size of your gadget graph. And what the subcube density will do is it will place an upper bound on what the value of dh can be. So as long as you pick dh to be smaller than this quantity, d over the subcube density, you will be able to argue there's very few.
Times not over.
And it's divided by. So if you, this is,
This number
this
is,
button is, and then,
is-
yeah.
sorry, this number is large, so.
Yeah.
Maybe density is the wrong word, but
yeah, I guess, yeah, sorry. So this is like a, yes, this is larger than 1. It's going to be something like square root d or something like that. Yeah, so as long as you can show that dh is smaller than this quantity, or as long as you pick dh to be smaller than this quantity, then you can avoid collisions of this form.
Small than square root d. D was the capital D, right?
Yeah, capital D. So actually, okay, maybe in general, this is actually going to be something like d to the 5x, but it's going to be, yeah. I will talk about it in a second. I guess the important thing here is there's a property of the cubical complex, which will give you some restrictions on what you can choose your gadget degree to be. Okay. Cool. So that's the first type of collision. The second type are going to be those occurring between different gadgets. Okay. Let's try to. So the goal is going to be okay. So let's say we already showed there's going to be very few bad gadgets. Let's say we're in a situation where they're all good gadgets. Okay. And our goal. So now we know that each of these good gadgets is going to have many different edges going to unique neighbors on the right within the gadget. We want to show these different cubes don't cancel each other out. Let's consider this case where you have a single middle vertex, a single gadget with a single cube in S. The single cube in S is going to send out dh different edges to dh different cubes here on the right. We'd like to show that these things all go to different unique neighbors. None of them are being canceled out. When can a cancellation occur? It can occur if you have another gadget, also in good, that overlaps on that cube. I guess you have a possibility that this one will be hit when you go from a cube here to here, and then you'll get a collision. So in particular, the number of collisions that your this gadget here will experience is upper bounded, or like maybe given by the number of neighbors of the form if you go from U to R back to the good set. So if you want to argue that most of these DH guys actually go to unique neighbors, it suffices to have some equality of the form DH is bigger than this number of good to R to good neighbors. What is a good to R to good neighbor? Well, let's recall that the good set is going to be some vertices. When you go up to R, you go up to a cube. Okay. And then when you go down back to good, you go to another vertex. Okay. So the number of such neighbors is actually the number of neighbors of this form. The number of distance k/2 neighbors within your cubical complex. Okay. Maybe let me just rewrite the exact same thing, just in slightly different terminology. So it's the same, this thing is exactly the same as DH is bigger than the number of lengths k/2 paths in any vertex set good, or small enough set good.
You need to be bigger or way bigger?
Way bigger,
Way
like
bigger.
maybe, yeah, like 1/epsilon times. We'll call this quantity the path density of the cubical complex. It's another property of the cubical complex you can try to bound. And if you get a bound on this guy, this will give you a lower bound for the value of DH.
So, the number of length k over two paths. For any length k over two path, you get this kind of ping pong thing. Or only the ones that correspond to.
So not necessarily, yeah, so, yeah, so I guess like maybe going back, oops. Yeah, so the question I guess was like, will you always get collision here if you have such a length k over two paths? And the answer is like, not necessarily, but we don't know how to argue that you don't.
It's like length k over two in the cube, so we just move to another Hadamard code word.
You need to move to another code word. It's
Yeah,
not just
another
any
code word.
flipping of half
Yeah.
the bits. That's not.
It is flipping of half the bit.
No, but it's not a random flip.
No, it's a random,
Oh, no,
no,
that's
very
much
normal
fewer.
by another Hadamard code word.
Right.
Yeah.
Wouldn't that help your count?
Is
You're only allowed to add, you're at a Hadamard code word, you're only allowed to add another code
Yeah.
word. You're not allowed to choose any k over two path you want, or am I getting it wrong?
Oh, I mean, so in the cubical complex itself, like each of the directions has some generators, right?
Yeah.
So like if you wanted to go from here to here, it's like you just need to choose generator this direction and generator this direction.
And that dominates the count anyway, is that what? you're
Compared to
saying?
what?
Compared to the. Okay, maybe I'll ask you offline.
Okay.
I wanna help you.
Okay,
But no, I think it's an important question. Don't you, I mean, this length k over two paths is itself determined by some Hadamard code word, right?
yes, yeah, sorry, within the Hadamard, yeah,
Yeah, it's not an arbitrary k over.
sure, yeah, okay, you're right, yeah. Yeah, yeah.
Just.
Okay.
The only k places to go.
There are only k places to go to,
Sure, yeah.
so it's like case, yeah.
Yeah, I guess we're always only considering small sets that are take place in the Hadamard
Okay.
locations, yeah.
Sounds good.
So we call the properties of path density and just place a lower bound on DH.
I think calling it the path is, I mean, I guess.
It's
Oh, okay,
confusing,
I see, I see.
because
It's like-
it's
it's
not
like a-
about paths.
It's a Hadamard path.
It's about code words,
Sure,
yeah.
yeah.
You
But I guess
can go
it's-
to all other Hadamard
But
code
it's-
words.
But, okay, but I think the reason they call it path is because once they choose the other code word, they still have a choice of generator per dimension, and that dominates the count.
Yeah, that's true. Yeah, you can like, yeah, yeah, I
You
guess like.
decide to
the-
go on the
It's a
x-axis.
billion.
No, you decide to go on, no, it's not a billion, you go on the x-axis, you need to choose a generator here.
And you may go in a different cube than this one, of course, yeah.
Oh, yeah, I guess you could have also gone this way, but like a choice of this,
Different ways, maybe.
no, but actually like because the cubical property of the complex, like a choice of these two edges corresponds exactly to a single choice of two edges that direction.
Yeah, but even if you chose these two directions and you told me what generators, the order matters.
Yes, well,
No,
not really, it's like the set of things you can reach is the same, no matter which way you go.
The order
No,
is,
no, no.
at least the order doesn't
It's a
matter.
billion.
No,
It's
of course.
not a billion.
No, but
If you
like,
choose A1 and then
Arbitrary order.
A2 and you go somewhere,
I
it's
think-
not the same as if you go A2 and
I
then
think
A1.
the fixed
But
count,
there's a unique way A1 prime and
It doesn't
A2
affect
prime.
your
Yeah.
That's a property she
the sense that like,
defined.
complete the generators.
It's really a billion.
It's not a billion.
I think
No,
it's unique.
it's not a billion, but
It's
you can-
unique. It's not-
You can think of it as a really few
Okay,
words.
fair enough.
Right, like what you need to consider is like choose a canonical.
Sorry that we're spamming.
Oh, no, it's good, yeah. Oh, we're almost,
We want to-
we'll
we're
give
trying
you
to
more time.
understand.
okay, well, it's almost done, so I think, yes, it's good.
Gives you a weight k over two vector.
I will just say you can get to all
Generator.
other Hadamard words
Yeah.
except for one. Right.
On the generators.
I don't know, from no, to all of them, yeah.
Oh.
Yeah. All of them.
That's why like the,
Wait,
No, no,
actually, I have
maybe
a question. I mean, okay, I'm always imagining that we're walking from like one Hadamard code word to the other Hadamard code word, right? And then like it's really clear that because of this subcube property that you can basically just choose kind of one meta path in like which generators and then go. what happens if you walk from like the code word to itself by just like doing?
So I guess this is like it's kind of a little bit different than the walk terminology in the sense we only care about like other neighbors, like we just don't think about the one neighbor like yourself. Like you care about like I guess like it's like in a graph is like you can go from like vertex to edge to vertex, but like we care about like number of neighbors, which are the other end of the edge. We don't care about coming back. Like we're counting neighbors, not looking at walks.
To pick a non-zero.
Okay, sorry, maybe just to answer, the thing we care about is the number of neighbors of this form, where you take such a walk. But we don't, like the walk itself is.
No, actually, I'm not entirely sure I understand.
It doesn't matter, epsilon will be bigger than K over DH. So it doesn't matter if you go to a self or something. K is much smaller than DH, and epsilon will be bigger than the ratio. So whether you go to yourself or not doesn't really matter.
Okay, I guess like collisions occur when you go from a vertex to a cube to a different vertex. You don't really get collisions when you go back to yourself, right? Because it's just.
You've already counted
You've
them in
already,
the same gadget.
Yeah.
The type.
Okay, so that's the thing.
Yeah.
If you go from something to yourself, this was already dealt with in a different case of the proof. So it's not. Okay.
they're different gadgets, yeah.
Right, like the promise that these are different gadgets will promise you that you only need to deal with things coming from different Hadamard code words, I guess.
Yeah.
Wait, actually, do I believe that?
It's because every cube can only contain one vertex of a given part in your cubical complex, right? You can't just.
Right. Okay, I believe.
Okay. Okay. Great, so we have a bound. So now we have two different bounds on what you can choose DH to be, right? So we said that the path density gave you a lower bound for DH, subpeak density gave you an upper bound for DH. As long as you can show this, like, so as long as you can show that the product of the two is much less than D, there will be a gap between these two where you can choose DH, okay? And if you can choose as a DH, then we've shown you can avoid both types of collisions, and then we're very happy. And then we're basically done.
The product?
Oh, it's just, I guess like this is
Defined.
D over subq density, and this is pi. You need there to be
Oh.
that's it. Yeah, that's it. Yeah. I guess this is logarithmic scale, not additive scale, or it could be either. I guess, but I guess maybe another thing about here is like there's some constants that we incur when you do analysis, like a bunch of like 2 to the k's and blah blah. So you'd like it to be like, I guess, much larger possible. So what we are able to show is that the path density in these in the cubical complex is d to the 1/4. Subcube density is d to the 5/8 for a particular choice of epsilon, which is 2 over root k. And as a result, we get 1 minus 2 over root k vertex expansion.
So DH is a small lossless expander you brute force to construct.
Yes, and that's, the DH is a degree of the, yeah.
Can you remind again what the subcube density is?
Let's see. This guy. So it's a number, I think maybe for now you can just think of it as it's epsilon. So it's the number of cubes that are entirely contained within your small set. And then maybe the epsilon is there to place like it's like a refined version where you want to count the number of cubes with like a large fraction, large meaning epsilon, fraction of vertices in your set.
Okay, so if I think of the complex, you color some of the vertices, this is U. And then you want to know how many cubes are completely or kind of
Partially.
epsilon contained inside this. So if like it's some kind of sampling property, you want to say that since the set is small, most cubes should see a fraction of this set that's proportional to its size, and exceeding it, going all the way to epsilon, in this case epsilon is large, it makes it I don't know, unlikely, and that's this is the sigma, that's what sigma is counting. So it's kind of a sampling
Yes.
property.
So this is this still is the Ramanujan, of course, Ramanujan property of the complex, but as a graph.
Yes, like you want to show things are not very clustered.
I mean, where do you get the 5/8?
Okay, well, so I was actually not gonna tell you how the analysis goes. Maybe you can have us offline if you're interested.
Yeah, sure.
I think that's actually not the hard part. Like you can. Those
It's
things,
not
but-
that I was asking to see some calculation, I haven't.
Yeah, let me.
But I just wanted
Why
to,
don't you get scrolled?
yeah,
Yeah,
if
yeah,
it was
yeah.
Ramanujan, you would
Yes.
expect some nice.
Yes, I have one more slide. So this is answering why the cubical complex, like why why can't you just do something like Ramanujan graphs? Like Ramanujan, like what's wrong with Ramanujan graphs? Oh, there's a thing missing. Okay, there's supposed to be this quality here up there, but I don't know where it went. Maybe I'll show it later. So yeah, because you have these two properties you want to show us in D. Okay, so for Ramanujan graphs, the key equation, which isn't written there, is actually false. In particular, if you only have like this is maybe a little bit vague, but hopefully you'll be convincing enough. But if you only have a one-dimensional graph, both the path density and the subcube density are both basically going to be small set edge density. What is that? It's like where you take a graph, you restrict to a small set of vertices, and you look at the induced subgraph, and you look at the average degree there. So this is like the average degree in small sets. Okay. And it turns out that there exist Ramanujan graphs where small set edge density is root D.
Are these the Kaufman-Camber?
For instance, yeah.
I see. So it still could be true for for other.
It could be true, but we don't know how to show it. Yeah.
But I mean, it's just because you count path density and subgroup density. I mean, in our old one-sided, we do use Ramanujan. We just count other things that make Ramanujan be sufficient. So for your inequality, one dimension.
Yeah, so actually like kind of the main thing that makes this problem harder than or I don't know if it's harder, but like it's like different than the one-sided version is that for like your work, you only need something of the form like this inequality needs to hold, and you can pick DH kind of anywhere in this range. Whereas we have this second competing inequality that kind of we need to also like bound.
Yeah, our graph is not really symmetric, so.
Sure. Okay.
I want to ask again about the Ramanujan graph. So even in the example where you get the small set edge density root D, does that mean, and you use this gadget, you use just your construction, it will be the inequality phase or actually lossless expansion phase?
Inequality fails. We don't know how to. I mean, there's gaps, but we don't know how to certify that it actually has loss expansion. Yeah. So like I guess our analysis will not work for giving you loss of expansion. It's very likely that it will have loss of expansion. We just can't show it.
Yeah, here in this example, cubes are edges, right? In this one-dimensional case, cubes are really edges.
Yeah, that's why these things are both
Yeah.
edge density. Yeah.
So in the, okay, I guess.
Okay. Okay, yeah. So maybe talk about, and so the point is both these things are root D, so you have root D times root D is root D, not much less than root D. So, okay. Cubical complex. Here's one way to state the gain we get. When you have higher dimensional structure, it lets you control like higher dimensional densities. So instead of looking at just edge density, or small set edge density, you can now look at small set like triangle density or small set tetrahedron density or higher dimensions. And so this allows you to compare so I guess path density is always going to be something like edge density. And this thing, you can now think of it as tetrahedron density. So now you're no longer comparing edges to edges, and you can kind of hope to get a gain that way. So maybe that's, I guess I did, there it came, okay. So I did want to mention one thing, which is, it disappeared again. Okay. So there is a way you can get a naive upper bound on subcube density using spectral bounds alone of the one skeleton. Here's how you can do it. You can take the path density in your small set, and then you can multiply it by the number of ways to complete the path to a cube. This is a way you can obtain a bound on a subcube density using just what you know of the one skeleton. Unfortunately, if you do something like this, you'll get something like d to the 3/4. And this is not going to be good. Why? Remember, I told you that this path density here, we got to be d to the 1/4. This subcube density, this naive bound, is going to give you the remainder of the space, the other d to the 3/4. So we won't get a separation here, and we won't be able to pick DH correctly. Yeah, so this is barely not good. But the really nice thing about like, HDX and also cubical complexes is like the local link with local structures have more additional structure you can use to get better bounds than this naive approach. So I guess that's all I'm saying. Yeah. So the links have some additional structure, which we actually are able to use to get better bound than D to the 3-quarter.
So what is the dimension of your cubical complex?
So dimension is going to be like 1/epsilon squared, I think.
Where is it used in all these calculations?
Yeah. So let's see. Oh, sorry, I went back too far.
You had to expand in one over
Yeah.
with K, right?
Yeah, so it's just this. So you to analyze the density for a particular choice of epsilon. This is a epsilon we were able to show for. So this gives you this.
So the like the path density and the subcube density doesn't like doesn't depend on the dimension. It's just
Okay, so there's like a 2 to the k somewhere, and
okay.
and like d you would need to pick to be like exponential k. I don't know. There's those things.
Why epsilon changes the density calculation?
Yeah, so for instance, if you take epsilon, let's say it's 1/k, so you want to ask how many cubes have exactly one vertex in your set. So very weak bound, like you can take a single vertex and you can take all the possible cubes. And that'll give you like capital D number of such cubes,
Oh, I
and
see.
so this pink thing will be all the way down to 0.
It's a sampler, right? So there's always two parameters. How far are you from the expectation and what's the probability of being that far?
Okay, so I was so epsilon only participates in the definition of subcube density, not the path density. Okay,
Yeah.
yes.
That's actually all I had to say, so if you guys. I guess it came back up again.
Okay, so
Oh, yeah, so it's.
you have down
Maybe you-
the last slide.
Okay, sure, I can just say it. So yes, I guess the other thing we've done is we've shown that you can take, that basically it's like cubical complexes act as a good high dimensional amplifier for the property of lossless expansion. So the way you can go from local to global. So I guess a few open questions. So one is like, I guess we've seen how you can use HDX to amplify other properties like local testability or distance, or I guess many of you probably have more applications, like like PCP stuff or yeah, but like, so I guess the question is like, maybe we can find more applications where HDX allows you to amplify the desired properties you want. Another question is the D versus like the epsilon trade-off. So right now we're getting something like, okay, maybe even in the one-sided case, the best we know right now is epsilon is 1/√D, but the best you can hope for is 1/D, which you can achieve this random.
One over your degree is K times DH, no? And epsilon is just 1/squared K. So
For
this is really, the total degree is exponential enough.
for us, yes.
Yeah.
So this is a one-sided case, the best you can do. We know that it's,
Yeah, sorry, one-sided,
Yeah, and
yeah.
you're right. And then for us, we're getting something like epsilon is 1/log D. Yeah.
Was Louis Golowich's paper the one-sided one? It was only 1/D?
Yeah, I think like the CRVW got like 1/cube root of D.
That's the one. Okay, yeah.
Yeah.
Some weird.
Yeah, so then I think Louis got the 1/D.
Okay, that was 1/D or something. Maybe I'm wrong.
We shouldn't have it yet, I think. But yeah, I think it's a pretty interesting question. And then also there's unbalanced case. I guess, yeah. Like if you have polynomial imbalance between the left side and the right side. We don't know how to construct constant degree expanders. And that's all. Okay, so now I'm actually done.
We can have some more questions.
Sorry, do I understand right that the construction, it's not recursive, you just pick the base graph and the gadget? Great, okay, thanks.
Any more questions?
So you said your graph, your lossless expander is not Ramanujan graph. Is it because like the left and the middle part is not like the graph between left and middle and the right are not Ramanujan?
I mean, it's the cubical complex is like, I think the main issue is like, if you look at some walks in this graph, you'll always get some sort of like sets will come back to themselves, which are like 1/k probability or like 1/d probability.
I see, so it's,
Like the K and D trade-off is pretty bad.
so it's analyzed explicitly based on your construction, not by some properties of your gadgets, like during your construction, because those failed, and that's why you don't get a Ramanujan graph. It's because you did the calculation.
Yeah, we just like found a bad set. We found a bad set that was not very expanding.
I see.
It gives you some bound on the eigenvalues.
I see. So is there any properties in the construction that would guarantee the Ramanujan? Property event? Like for example, if some stuff exists or some additional properties exist for the cubical complex or something, it will be in Ramanujan as well.
I don't know, actually. It's a good question. Yeah, so I guess like one question could be objected to the slide is like, could you get a lossless expander which is also near Ramanujan or something? I think we know how to do that, but we haven't written it. I don't know. Is that I don't know. Maybe it's interesting, but yeah. Yeah.
Can you get any like non-trivial imbalance that's interesting for extractors or things like this?
We can
I
only
guess
get
for
constant
log-
imbalance.
What?
We can only get constant imbalance.
Even like log is not the.
We don't know how to do that, no. Well, maybe
What's the
log
barrier?
is,
You
maybe
can
log is-
force over log size.
yeah, maybe a log is okay. Yeah, I need to check, but it's possible, yeah.
Okay, by the way, before we finish, Rachel is here until,
Wednesday morning.
so today and tomorrow, if people want to talk to her, and maybe we'll get you to explain to us, edge density.
Yeah.
All right, thank you very much.